The raw power and beauty of storms have captivated the human imagination since we first looked toward the horizon. Let us drift into the fascinating science behind these atmospheric wonders. We begin by realizing that we live our entire lives at the bottom of a vast, invisible ocean of air. As you settle in to let this knowledge wash over you, please take a gentle moment to like and subscribe for more sleep-friendly learning. This ocean, our atmosphere, is a fluid system behaving remarkably like water, swirling and flowing around the obstacles of mountains and valleys. It is composed of a delicate mixture of nitrogen, oxygen, and trace gases that wrap the planet in a protective blanket roughly 300 miles thick. Despite its invisibility, the atmosphere is incredibly heavy, with the total weight of the air surrounding Earth estimated to be around 5.5 quadrillion tons. We do not feel this weight crushing us because the air inside our bodies exerts an equal and opposite outward pressure, allowing us to move effortlessly through a medium that presses down with nearly 15 pounds of force on every square inch of our skin. All of the weather we experience, from the softest mist to the fiercest gale, takes place in the lowest layer of this envelope, known as the troposphere. This layer extends only about 7 miles up on average, yet it contains nearly 80% of the atmosphere's total mass and almost all of its water vapor. The engine that drives the movement within this layer is the sun, which heats the planet unevenly. Because the Earth is a sphere, the equator receives direct, concentrated sunlight, while the poles receive sunlight at a glancing angle, spreading the energy thin. This creates a permanent temperature difference that the atmosphere is constantly trying to resolve. Warm air at the equator becomes less dense and buoyant, rising high into the sky and creating a zone of low pressure near the surface. Nature abhors a vacuum, so cooler, heavier air from surrounding areas rushes in to fill the void left by the rising warm air. This simple exchange, essentially a massive convection current, is the heartbeat of global weather circulation. As this air moves, it carries energy in the form of heat and moisture, transporting it from the tropics toward the poles in a ceaseless quest for thermal balance. However, the journey of the air is complicated by the rotation of the Earth itself. As our planet spins on its axis, it drags the atmosphere along with it, causing the moving air to deflect and curve rather than flowing in a straight line. This phenomenon, known as the Coriolis effect, is the invisible hand that shapes straight winds into spiraling vortices we recognize as storm systems. It causes winds to twist to the right in the northern hemisphere and to the left in the southern hemisphere, orchestrating the global dance of cyclones and anticyclones. Another critical factor in this atmospheric recipe is the lapse rate, which refers to the rate at which air temperature decreases as you move higher in altitude. Generally, for every 1,000 feet you ascend, the temperature drops by about 3.5 degrees Fahrenheit. This cooling effect is vital because it acts as the trigger for condensation. Water vapor is invisible to the naked eye, a gas that exists freely in the air around us, but its presence is governed strictly by temperature. Warm air acts as a spacious container for this vapor, capable of holding vast amounts of hidden water, while cold air loses that capacity. When warm, moist air rises and encounters the chill of the upper troposphere, it is forced to release its moisture, transforming invisible gas into visible cloud droplets, setting the stage for the dramatic architecture of the sky. This architecture begins at the molecular level, where a secret ingredient is required to bridge the gap between invisible gas and the white, billowing structures we admire. Pure water vapor, surprisingly, struggles to condense on its own without a surface to cling to. It requires a seed, a microscopic platform known as a condensation nucleus. These tiny particles are everywhere in our atmosphere, consisting of ocean salt spray, microscopic dust from distant deserts, pollen from forests, or even ash from volcanoes. It is a poetic thought that every white cloud floating over a green meadow may hold at its center a grain of sand that traveled thousands of miles to be there. When the sun warms the earth, bubbles of warm air known as thermals break free from the ground and begin their ascent, carrying both the water vapor and these microscopic seeds upward. As this warm air rises, it enters regions of lower pressure, allowing it to expand. This expansion causes the air to cool, and once it reaches the dew point, the invisible vapor suddenly grasps on to the dust or salt particles, instantly reverting to liquid water. This is the moment a cloud is born. The flat bottom you often see on a fluffy cumulus cloud marks the precise invisible altitude line where the temperature has become cool enough for this phase change to occur. While these floating cotton balls appear as light as a feather or a stray thought, they are deceptively massive. If you were to take a single average-sized cumulus cloud, the kind that looks like a friendly sheep grazing in a blue pasture, and weigh the water suspended within it, the scale would read approximately 1.1 million pounds. To visualize this mass, imagine 100 large elephants clustered together, floating silently and effortlessly above your head. Despite this immense weight, the cloud does not fall because that weight is distributed among trillions of microscopic droplets, each so small that the slightest updraft of rising air is enough to keep them suspended in defiance of gravity. For the vast majority of these clouds, their existence is peaceful and fleeting, known to meteorologists as fair-weather cumulus. They are the decorative pillows of the troposphere, bubbling up in the morning as the ground warms, drifting lazily across the horizon, and often evaporating back into invisibility as the sun sets and the lifting power of the heat fades. They do not rain, they simply exist to cast shadows and reflect sunlight. However, in the life of a storm, this peaceful suspension is merely the beginning. If the atmosphere is unstable enough and the updrafts continue to feed the cloud with more heat and moisture, the gentle cumulus will not evaporate. Instead, it will begin to grow vertically, towering higher and higher, transforming from a fluffy ornament into a towering engine of energy, waiting for the critical moment to release its heavy burden back to the earth. Inside that towering white giant, a silent threshold is crossed. The microscopic water droplets, previously content to float on the gentlest updraft, begin a dance of accumulation known as coalescence. It is a process of merging, where one tiny sphere bumps into another, and instead of bouncing apart, the water tension pulls them together. They fuse, growing heavier with every collision. This happens millions of times, a cascading domino effect of moisture until the droplet becomes too heavy for the rising air currents to support. Gravity finally asserts its dominance, claiming the water for the earth below. As these travelers begin their descent, they defy our collective artistic imagination. If you were to draw a raindrop, you would likely sketch a teardrop shape, tapered at the top and rounded at the bottom. But physics paints a different portrait. Small raindrops remain spherical, held tight by surface tension, much like a bead of mercury. However, as they grow larger and pick up speed, the air rushing up against them acts like a sculptor's hand. The pressure flattens the bottom of the drop, while the top remains rounded. A falling raindrop actually resembles the top half of a hamburger bun, or perhaps a small liquid parachute, constantly shifting and wobbling as it battles the air resistance. If the drop becomes too large, roughly the size of a jelly bean, the air pressure will eventually punch a hole through the center, splitting the drop into smaller, more stable spheres, ensuring that the sky never drops heavy water balloons on our heads, but rather a uniform scatter of rain. The speed of this descent creates the rhythm we know so well. It is not a uniform velocity, but a symphony of different tempos. A very fine drizzle falls slowly, drifting more than plummeting, while a standard raindrop falls at roughly 14 miles per hour. The largest drops can race towards the ground at over 20 miles per hour, hitting the pavement with that distinct heavy percussion. Speaking of that sound, do you prefer the heavy drumming of a summer storm or the quiet, steady whisper of a gentle shower when you are trying to sleep? Yet not every journey ends in impact. There exists a phenomenon that is arguably more beautiful than the storm itself, a ghost of a rainstorm known as virga. Often seen in the American West or during high-altitude sunsets, virga occurs when rain falls from a cloud but encounters a layer of dry, warm air beneath it. The air is so thirsty that it absorbs the rain before it can ever touch the ground. From a distance, this looks like trailing wisps of gray or white hanging from the cloud base, resembling the tentacles of a jellyfish drifting through a sky-blue ocean. It is rain that is seen but never felt, a suspended conversation between the cloud and the air. Yet on this cycle of evaporation, the air cools significantly, sometimes creating a rush of cold wind that eventually reaches the surface, the only physical evidence that rain attempted to fall, leaving the ground dry while the sky remains active. Even when the rain doesn't touch the ground, or perhaps especially when it is just about to, the air itself changes character, becoming heavy and charging the atmosphere with a specific, undeniable perfume that alerts us to the weather long before the first drop falls. This is often the first sign of an approaching storm, a sweet, pungent zing that acts almost like a chemical alarm bell. That sharp metallic smell that precedes the clouds is actually the smell of ozone.
As lightning tears across the sky, or even as electrical charges build up unseen within the cumulonimbus towers, the immense energy splits nitrogen and oxygen molecules in the atmosphere. These separated atoms sometimes recombine into groups of 3 oxygen atoms, creating O3, or ozone. Downdrafts from the storm front then push this gas from the higher altitudes down to the surface, bringing that distinct chlorine-like clean smell that we associate with a fresh breeze. Once the rain actually begins to strike the dry earth, the scent profile shifts dramatically, becoming richer and more grounding. This familiar aroma has a beautiful name, coined only as recently as 1964 by 2 Australian researchers, Isabel Baer and Richard Thomas. They named it petrichor. The word is constructed from the Greek petra, meaning stone, and ichor, the golden ethereal fluid that was said to flow in the veins of the gods in Greek mythology. It is, quite literally, the blood of the stone. Despite the poetic name, the source of this scent is microscopic and biological. The primary component is an organic compound called geosmin, which translates simply to earth smell. It is produced by a specific type of soil-dwelling bacteria known as streptomyces. During dry spells, these bacteria produce spores for survival, and when the rain arrives, the moisture helps release the geosmin into the air. What is truly fascinating is our biological relationship to this molecule. Human beings are incredibly sensitive to geosmin, capable of detecting it at concentrations as low as 5 parts per trillion. To put that in perspective, we are far more sensitive to the smell of rain-soaked earth than a shark is to the scent of blood in the water. One might wonder if this sensitivity is an evolutionary echo, a survival mechanism that once guided our ancestors across arid landscapes toward fresh water. Do you have a specific memory of a summer afternoon where this smell signaled the end of a heat wave, bringing a sense of relief along with the clouds? Petrichor is a complex bouquet, however, and geosmin is accompanied by oils secreted by plants. During dry periods, plants release specific fatty acids and oils that accumulate in the soil and on rocks. These oils actually serve to inhibit the growth of seeds and roots, preventing competition for scarce water. When the rain finally falls, it kicks these oils up into the air, blending them with the bacterial notes. The mechanism of how this scent reaches our noses is a marvel of physics in itself.
Using high-speed cameras, scientists have observed that when a raindrop hits a porous surface, it traps tiny bubbles of air at the base. These bubbles shoot upward and burst, fizzing like a glass of champagne, ejecting aerosols carrying the scent. The lighter the rain, the stronger the scent often is, as heavy downpours tend to drown the aerosols before they can escape, washing the perfume away rather than letting it linger. While that earthy perfume settles near the ground, a far more volatile transformation is taking place thousands of feet above, deep within the dark, churning heart of the thunderhead. Inside these powering cumulonimbus structures, the atmosphere becomes a massive engine of friction. As updrafts sweep violently toward the stratosphere, they carry tiny water droplets that freeze into microscopic ice crystals. Simultaneously, heavier, soft hail pellets, known as graupel, fall downward through the cloud. In this chaotic vertical dance, the rising crystals and falling graupel collide billions of times, creating a static charge in the same way you might build up electricity by shuffling across a wool rug on a dry winter day, though on a scale that defies imagination. Through this relentless friction, the cloud becomes a polarized battery. The lighter ice crystals carry a positive charge to the very top of the storm anvil, while the heavier graupel drags a negative charge to the base, creating a brooding electrical shadow that hovers over the landscape. The air between the cloud and the ground acts as an insulator, a barrier preventing the current from flowing. But as the charge builds to colossal levels, the insulating properties of the air begin to break down. Nature desperately seeks equilibrium, and eventually the tension becomes too great to contain. The release begins not with a bang, but with a silent, invisible search called a stepped leader. This is a faint channel of negative energy that emerges from the cloud base, moving downward in rapid, hesitant jumps. It is a pathfinder, branching out like the jagged roots of an inverted tree, feeling its way through the atmosphere to find the path of least resistance. It pauses every 50 meters or so for a fraction of a microsecond, changing direction, zigzagging through the sky, unseen by the human eye. As this leader approaches the Earth, the ground responds. Positive charges pool on the highest points, treetops, church spires, and mountain peaks, sending up invisible tendrils called streamers to greet the incoming energy. When a downward stepped leader and an upward streamer finally lock together, the circuit is closed and the sky ignites. This is the moment of the return stroke. Contrary to how we perceive it, the brilliant flash of light we see actually travels upward from the ground to the cloud, tracing the path laid out by the leader.
It happens at roughly 1/3 the speed of light, so fast that our eyes interpret the event as a single, instantaneous downward strike. The physics of this momentary connection are staggering. In that fraction of a second, the channel of air is superheated to approximately 50,000 degrees Fahrenheit. To put that into perspective, that is 5 times hotter than the surface of the sun, generated instantly in the cold rain. Yet perhaps the most surprising fact is the size of this conduit. While the blinding glow makes the bolt appear thick and massive, the actual channel conducting the electricity is often no wider than a human thumb, typically just 1 to 2 inches across. It is a razor-thin wire of plasma, the fourth state of matter, tearing through the sky with enough heat to explosively expand the air around it. This sudden displacement is what creates the shockwave we hear as thunder. Yet for all the drama of a cloud-to-ground strike, nearly 3/4 of all electrical discharges never actually touch the Earth. They remain imprisoned within the chaotic atmosphere above, leaping between regions of opposing charges inside a single cloud or jumping across the gap to a neighboring storm cell. We often call this sheet lightning, a gentle, diffuse illumination that lights up the cloud from within like a grand paper lantern, obscuring the distinct channel of the bolt and leaving us with only a soft, flickering glow that dances across the horizon. On warm summer nights, you might watch these silent flashes pulsing in the distance without ever hearing a sound, a phenomenon colloquially known as heat lightning. Though it has nothing to do with the temperature, the storm is simply too far away for the sound waves to survive the journey to your ears. Have you ever sat on a porch swing or looked out a bedroom window, mesmerized by that silent, rhythmic flashing on a humid night, wondering where the storm actually was? Originating from the positively charged anvil top of the storm rather than the base, these massive arcs can travel horizontally for miles before curving down to strike the ground in clear air, far from the rain and clouds, carrying nearly 10 times the current of a standard bolt. Even stranger is the baffling phenomenon of ball lightning, which for centuries was dismissed as a sailor's myth. Lighthouse keepers and pilots reported seeing glowing orbs of electricity, ranging from the size of a grapefruit to several feet across, floating eerily through the air or rolling along the ground. Unlike the millisecond flash of a standard bolt, these spheres can persist for nearly a minute, drifting horizontally and sometimes passing through closed windows or down chimneys before fizzling out or exploding, a mystery that modern science still struggles to fully reproduce in the lab. If we turn our gaze even higher, away from the ground and toward the blackness of space, we find the most mystical of all electrical events, the transient luminous events that occur high above the thunderheads. These were once the stuff of rumors, deemed optical illusions by pilots until they were officially documented in 1989. The most famous of these are the red sprites, vast jellyfish-shaped clusters of cold plasma that flash a deep blood-red color in the mesosphere, some 50 miles up. They're triggered by powerful lightning strikes below, reacting to the electrical imbalance by blooming upward into space with dangling tendrils that can span 30 miles across. Accompanying them are the blue jets, narrow cones of sapphire light that erupt from the tops of clouds and shoot upward into the stratosphere at supersonic speeds, like cosmic gyres reaching for the stars. Even more elusive are the elves, a whimsical acronym for immense expanding rings of dim red light that appear at the very edge of the ionosphere. These glowing halos can expand to 200 miles wide in less than a millisecond, a fleeting ripple of energy crashing against the ceiling of our world, proving that the storm we see from below is only the basement of a towering cathedral of light. While the light from these upper atmospheric events travels to our eyes instantly, the voice of the storm is bound by the leisurely speed of sound, creating that characteristic pause that feels heavy with anticipation. When the bolt finally speaks, it is because the lightning has heated the narrow channel of air to 50,000 degrees Fahrenheit, 5 times hotter than the surface of the sun, in a fraction of a millisecond. This incredible and violent injection of energy causes the surrounding air to explosively expand, creating a supersonic shockwave that travels outward in all directions, eventually decaying into the acoustic vibration we know as thunder. It is a sound that evokes a deep primal comfort for many of us, a signal that nature is in motion while we remain still. I wonder if you have a distinct memory of a specific storm, perhaps one where you sat safe and dry by a window, listening to the rain tap against the glass while thunder rolled across the hills in the distance. Let me know in the comments if that low, rhythmic rumbling helps you drift into a deeper sleep.
The specific texture of that sound, whether it arrives as a sharp, terrifying crack or a long, low mumble, tells a hidden story about the shape and orientation of the lightning bolt itself. A loud, instantaneous crack typically means the strike channel was very close, or that the bolt was oriented perpendicular to you, so that the sound waves from its entire length arrived at your ears at the exact same moment. More often, however, we hear a prolonged rumble, which is the result of simple geometry.
Because a lightning bolt can be several miles long, traversing the sky diagonally or vertically, the sound produced at the bottom of the channel reaches you significantly sooner than the sound produced at the top. This delay stretches a split-second explosive event into several seconds of rolling noise. As the bolt zags through the sky, it creates distinct segments of sound, which is why thunder often pulsates with louder claps amidst the growl. You are hearing the sound radiating from the sections of the bolt that are roughly parallel to your position. We have learned to use this delay to measure our safety, counting the seconds between the flash and the bang. Since sound takes roughly 5 seconds to travel 1 mile, a 10-second gap places the lightning 2 miles away. Yet, there is a fascinating limit to how far this acoustic performance can travel. In reality, this is simply a normal storm that has crossed into the silence zone. As sound waves travel through the atmosphere, they encounter layers of air with different temperatures and densities. Because sound moves faster in warm air than in cool air, and the air near the ground is typically warmer than the air higher up during a storm, the sound waves are refracted or bent upward toward the sky. This bending creates an acoustic shadow starting about 10 to 15 miles from the storm, where the thunder creates a canopy of sound overhead that never actually touches the ground, leaving the distant observer in a quiet world of silent, flickering flashes. Yet within that silence, or perhaps just beneath the horizon where the lightning flickers, resides the rarest and most organized member of the thunderstorm family, the supercell. While most summer storms are messy, chaotic clusters of rising air that live and die within an hour, the supercell is distinct because it possesses a deep, persistent rotation, behaving less like a fleeting weather event and more like a solitary, breathing giant with a lifespan of its own. At the heart of this atmospheric beast lies the mesocyclone, a colossal column of air that rotates vertically, often spanning 2 to 6 miles in width, acting as the primary engine that drives the entire system. If you were to observe a supercell from a safe distance across the plains, you might see this rotating updraft clearly, appearing like a sculpted cylinder or a twisted barber pole, with distinct bands of clouds spiraling upward in a slow, hypnotic rhythm that belies the immense violence hidden within. What makes this structure so architecturally successful, allowing it to persist for hours while other storms collapse, is the way it manages its own airflow. In a standard thunderstorm, the rain falls directly back into the updraft, cooling the air and effectively choking off the storm's fuel source. But the supercell is tilted by powerful winds high in the atmosphere. This tilt ensures that the updraft and downdraft remain completely separate, allowing the storm to inhale warm, moist air from the front while exhaling rain and hail out the back, creating a self-sustaining cycle that can traverse hundreds of miles of open country. As this updraft feeds on the humidity of the evening, it rockets skyward at speeds that can exceed 100 miles per hour, rising higher than the highest mountains and eventually soaring past the cruising altitude of commercial airliners, reaching heights of 50,000 feet or more. These storms are so tall that they eventually run out of sky, hitting the invisible ceiling of the troposphere known as the tropopause, a boundary where the air temperature stops cooling and begins to warm as it enters the stratosphere. When the rushing column of white water vapor hits this ceiling, it has nowhere to go but out, spreading horizontally in all directions to create the classic flat-topped shape known as the anvil. This massive canopy of ice crystals can fan out for 100 miles, often drifting far ahead of the storm itself to blot out the sun or moon, casting a premature twilight over the land below. In the most intense supercells, the updraft is so powerful that it momentarily punches right through that atmospheric ceiling, creating a small, solid dome called an overshooting top that rises visibly above the flat anvil, a clear sign that the storm is operating at peak efficiency. It is a testament to the sheer energy contained within our atmosphere, a towering structure of wind and water that rivals the grandeur of any mountain range on Earth, yet is built entirely of vapor and vanishes without a trace when the night is over.
Deep within this architectural marvel of air, a fascinating paradox begins to take shape, one that defies the logic of the summer season. While the air near the ground may be sweltering, thick with the heavy humidity of July or August, the upper reaches of the storm cloud are piercingly cold. It is here, in the turbulent heart of the thunderhead, that the formation of hail begins, creating ice in the very middle of summer. It starts with a tiny seed, perhaps a speck of dust or a small frozen droplet known as a graupel, caught in the immense power of the storm's main updraft. This upward river of wind is so strong that gravity temporarily loses its grip, and the tiny particle is suspended, hovering in the freezing darkness. As this embryonic stone floats there, it encounters supercooled water droplets, water that is actually colder than freezing but remains liquid until it touches a solid surface. Upon contact with the ice seed, these droplets freeze instantly, adding a new layer to the stone. But the journey of a hailstone is rarely a straight line. It is a chaotic, tumbling voyage, tossed about by the storm's internal winds like a sock in a dryer. If the updraft weakens or the stone drifts to the edge of the rising air, it begins to fall toward the warmer, lower sections of the cloud. Here, it collects a coating of liquid water, only to be caught once again by a renewed gust of wind that flings it back up into the freezing upper atmosphere. This cycle of falling and rising, of melting slightly and freezing again, creates one of the most beautiful hidden features of hail. If you were to slice a large hailstone in half, you would see concentric rings, remarkably similar to the growth rings of a tree. These layers tell the biography of the stone's travels. A layer of opaque, milky white ice indicates a time when the stone was high in the cloud, where it was very cold, causing water to freeze so rapidly that tiny air bubbles were trapped inside. Conversely, a layer of clear ice reveals a time when the stone was in a slightly warmer part of the storm, allowing the water to freeze slowly and release the air bubbles, creating a transparent shell. If you have ever been safely tucked inside while hail drummed a rhythm on your roof, or perhaps watched these white stones bounce off the pavement, let me know what that sounded like to you in the comments. For many, it is the ultimate sound of being safe indoors. Eventually, the stone becomes the victor in its battle against the wind. It grows too heavy for even the strongest updraft to support. When a hailstone reaches the size of a golf ball or a grapefruit, it is a heavy, dense object, and gravity finally reclaims it. It plummets toward the earth, reaching a terminal velocity that can exceed 100 miles per hour, racing downward to bring a touch of winter to a summer day. While the ice descends, something profound is happening within the air currents surrounding it. The falling precipitation drags cool, dense air toward the ground with it, creating a distinct and powerful current known as the rear flank downdraft. This descending column of air plays a critical role in the architecture of a tornado, acting almost like a sculptor's hand. As it reaches the bottom of the cloud, it wraps itself around the spinning updraft, pinching the rotation and forcing it to accelerate, much like the water in a bathtub spins faster as it approaches the drain. There's a principle in physics called the conservation of angular momentum, which you can see when a figure skater spins on the ice. As they pull their arms in tight against their chest, they spin faster and faster without adding any new effort. The storm operates on this same elegant rule. As the rear flank downdraft wraps around the central mesocyclone, it compresses that rotating column into a tighter and tighter radius. The wide, lazy rotation of the supercell begins to focus into a tight, energetic spiral. This is often visible to the eye as a lowering of the cloud base, a feature known as a wall cloud, which rotates slowly and ominously beneath the main storm tower. As the rotation intensifies, the air pressure inside the vortex drops significantly. This drop in pressure causes the air to cool rapidly, and the moisture within it condenses instantly into visible water droplets. This is the birth of the funnel cloud.
It is essentially a cloud forming not by rising, but by spinning. It hangs from the wall cloud like a gray, twisting stalactite, reaching tentatively toward the earth. I wonder if you have ever sat on a porch during a summer storm, watching the clouds shift and change shape, feeling that unique mix of awe and stillness that comes before the rain. It is important to note that the visible funnel does not need to touch the ground for a tornado to be officially present. The circulation creates a tube of wind that extends downward invisibly, often reaching the surface before the condensation cloud does.
The moment that invisible column connects with the surface, a tornado is born. We often see this first not as a funnel touching down, but as a swirling cloud of dust and debris rising from the ground to meet it. The connection completes the circuit, bridging the sky and the soil. Sometimes the condensation funnel, the smooth gray cone, never fully extends to the ground, yet the strong rotation is there, marked only by the swirling earth beneath it. In other moments, the funnel is distinct and solid, an opaque tube of condensed vapor shielding the interior from view. Inside that wall of wind, the speeds can be immense, concentrated in a very small area. A supercell thunderstorm can be tens of miles wide, a massive atmospheric engine covering entire counties, yet the tornado itself is often incredibly localized, focusing that immense energy into a point that might be only a few hundred yards across. It is a phenomenon of extreme concentration where the chaotic energy of the atmosphere creates a structure of physics-defying precision. This physics-defying precision creates a catalog of oddities that often sound like tall tales until the science confirms them. For decades, curious observers have reported phenomena that seem to violate the rules of interaction between solid objects, such as pieces of soft straw driven deep into telephone poles or blades of grass embedded in tree bark. These anomalies occur because at sufficiently high velocities, the inertial forces of the lighter objects allow them to act like rigid projectiles, piercing denser materials before they have a chance to crumble or bend. These curiosities led to many attempts to explain the unexplainable, often resulting in advice that sounds logical but proves dangerous. Perhaps the most pervasive of these is the persistent belief that one must rush to open the windows of a home before a tornado hits to equalize the pressure. The logic suggests that because the atmospheric pressure inside the funnel is so precipitously low, a sealed house might explode outward like an overinflated balloon if the pressure isn't released. However, atmospheric scientists and engineers have thoroughly debunked this idea, revealing that it is not only unnecessary but potentially disastrous. Houses are not hermetically sealed environments. They have vents, chimneys, and incidental gaps that naturally allow pressure to adjust rapidly enough to match the environment. More importantly, the structural failure of a building is caused by the sheer force of the wind pushing against the walls and lifting the roof, not by the pressure differential. By pausing to open a window, one actually allows the high-velocity wind to breach the structure, increasing the internal pressure and making the roof significantly more likely to lift off. The time spent managing windows is far better spent seeking shelter in an interior room, as the storm requires no assistance in entering a building. Just as our understanding of how to survive these storms has evolved, so too has our understanding of their structure. We often picture a tornado as a single, smooth, gray cone, but the reality can be far more complex. Some of the most intense storms manifest as multiple vortex tornadoes. In these chaotic systems, the main funnel serves as a carousel for smaller, intense subvortices that rotate around the central axis. These smaller swirls can spin at speeds significantly higher than the main rotation, acting like planetary gears in a massive atmospheric machine. This phenomenon helps explain the erratic damage patterns often seen in the aftermath,
where one home is swept completely away by a subvortex, while the property next door, missing the path of that specific suction spot, loses only a few shingles. The location of these events is shifting as well, challenging the traditional maps we learned in school. For a long time, the public imagination fixed Tornado Alley firmly over the Great Plains, encompassing states like Kansas, Oklahoma, and Texas. While this region remains highly active, meteorological data from recent decades highlight a significant eastward and southward shift. This shift presents new challenges, as the terrain in these regions is often hillier and more heavily forested than the open plains, making the approach of these storms harder to spot visually. It reminds us that the atmosphere is a dynamic, living system that refuses to stay within the boundaries we draw on maps. Just as the land shapes the wind, the open ocean offers a different kind of canvas for these spinning columns of air. Out on the water, without the friction of hills or trees to slow them down, we witness the birth of the waterspout, a phenomenon that has baffled and mesmerized sailors for millennia. While it is easy to assume a waterspout is simply a tornado that has moved over water, nature often prefers more variety than that. There is a distinct category known as the fair weather waterspout, which is far more common and surprisingly serene. Unlike the violent tornadic waterspouts that descend from massive rotating supercell thunderstorms, the fair weather variety builds from the surface upward. They typically form in light wind conditions, beginning as a dark spot on the water, swirling into a spiral pattern, and finally lifting a spray ring of mist toward the cumulus clouds above.
They are often translucent, ghostly tubes of water vapor that dance silently on the horizon, sometimes appearing in groups or families, creating a surreal colonnade connecting the sea and the sky. Perhaps the most magical iteration of this occurs when physics meets biology in the dark of night. If a waterspout forms over a bay rich in bioluminescent plankton, specifically the species Noctulica scintillans, commonly known as sea sparkle, the vortex acts as a giant agitator. Because these tiny organisms emit light when disturbed, the churning motion of the spout excites the algae, causing the entire column of water and spray to glow with an ethereal neon blue light. It becomes a literal pillar of fire in the water, a towering beacon of cold light spinning in the darkness. A sight so rare and dreamlike that it feels more like folklore than meteorology. Speaking of these elemental displays, I wonder, when you close your eyes and imagine the raw forces of nature, do you find more comfort in the rhythmic sound of heavy rain or the crackling warmth of a campfire? While the glowing waterspout is a marvel of cold light, nature also produces a vortex of intense heat. We call these fire whirls, or sometimes fire devils. These are not storms that drop from the sky, but rather cyclones created by the Earth itself when the conditions are just right. They occur when intense heat and turbulent winds combine to form whirling eddies of air. The physics here is a perfect example of the conservation of angular momentum. As a wildfire burns, it generates a massive updraft of hot air. This rising column creates a low-pressure zone near the ground, pulling in fresh, oxygen-rich air from the surrounding area. If there is already a slight wind or shear present, that incoming air begins to rotate. As the updraft stretches the column of air vertically, the rotation tightens and accelerates, much like a figure skater pulling their arms in to spin faster. The result is a terrifyingly beautiful core of flame that can reach temperatures of 2,000 degrees Fahrenheit, spinning with the ferocity of a tornado, but fueled entirely by the heat of combustion. These fire whirls remind us that whether made of mist, light, or flame, the spiral is nature's preferred shape for energy in motion.
As we leave the solid ground and the frantic energy of fire, we drift out over the vast heaving expanse of the deep ocean, where the spiral takes on a grandeur that rivals the galaxies themselves. Here, in the tropical latitudes, the water acts as the fuel for the greatest heat engines on our planet. These are not merely storms, they are massive thermodynamic machines that convert the warmth of the sun stored in the ocean into mechanical energy and wind. To ignite such a colossal engine, the conditions must be precise. The ocean's surface acts as a battery, and it must be charged to a specific thermal threshold. Meteorologists have found that the water temperature must be at least 80 degrees Fahrenheit or 26.5 degrees Celsius to support a tropical cyclone. Furthermore, this warmth cannot be shallow. It needs to extend down to a depth of roughly 150 feet, ensuring that as the massive waves churn, they do not pull up cold water that would extinguish the storm's heat source. Once this thermal energy is released, it rises, carrying vast amounts of water vapor into the upper atmosphere. As the vapor cools and condenses into towering thunderheads, it releases latent heat, which powers the updraft even further, creating a self-sustaining cycle of rising air. But a rising column of air is just a thunderstorm. To become a giant, it must spin. This rotation is a gift from the planet itself. The Coriolis effect, caused by the Earth's rotation, imparts a twist to the rising air. In the northern hemisphere, this spins the storm counterclockwise, while in the southern hemisphere, it rotates clockwise. It's a fascinating fact of physics that this spinning force drops to zero at the equator, creating a narrow band around the waist of the world where these storms physically cannot form. When these systems organize and strengthen, humanity grants them names, titles that shift entirely depending on where they wander. It's a reminder of how culture shapes our understanding of nature, that the exact same atmospheric phenomenon has three distinct identities based solely on geography. If the storm spins over the Atlantic Ocean or the Eastern Pacific, we call it a hurricane. This name echoes through history, derived from Huracan, the storm god of the indigenous Taíno people of the Caribbean, a deity who commanded the wind. Yet, if that same storm were to cross the international dateline into the Western Pacific, it would lose its title and become a typhoon. The etymology here is a blend of history, likely rooting from Cantonese Dai Feng, meaning great wind, or perhaps the Greek typhon, a mythological monster associated with storms. Finally, in the Indian Ocean and the South Pacific, stripped of mythology, they are known simply as cyclones, a word drawn from the Greek kyklos, describing the coiling of a snake or the wheel of a chariot.
Regardless of the name, the structure remains the same. A sprawling white spiral with a calm, terrifyingly clear eye at its center, watching the world below. To enter this circle is to witness one of the most jarring atmospheric contradictions on Earth. While the storm rages with kinetic fury, effectively tearing at the ocean and the land, the center is a sanctuary of eerie stillness. The winds, which may have been screaming at 150 miles per hour just a few hundred yards away, suddenly drop to a light breeze, sometimes no stronger than a whisper. It is a silence that feels heavy, a sudden intake of breath in the middle of a scream. If you were able to stand safely on the surface of the sea, looking up from this center point, you would witness a phenomenon meteorologists call the stadium effect. It is a fitting name, for the walls of the storm rise up around you in a perfect circle, resembling the steep seating of a colosseum built by giants. These towering banks of white cumulonimbus clouds can reach 10 miles vertically into the atmosphere, creating a deep cylindrical tunnel that dwarfs any human structure. The walls are not smooth, but textured and turbulent, constantly shifting as the centrifugal force of the storm pushes the clouds outward, keeping the center open. What makes this clear center possible is a reversal of the storm's primary engine. While the rest of the hurricane consists of warm, moist air rising rapidly to feed the energy of the system, the air inside the eye is actually sinking. As this air descends from the upper atmosphere, it compresses and warms up, a physical process that evaporates clouds and dissolves moisture. This is why, in the middle of a dark, brooding tempest, you can look up and see a circle of perfect, brilliant blue sky during the day, or a field of uninterrupted stars at night. It is a window to the heavens, surrounded by a curtain of rain. This sinking air contributes to another defining feature of the eye, which is the plummeting atmospheric pressure. The eye contains the lowest pressure of the entire storm system, and in the most powerful super typhoons, it creates some of the lowest pressure readings ever recorded on the surface of the Earth. It creates a suction effect on the ocean below, causing the water to bulge upward in a gentle dome, distinct from the violent waves crashing in the eye wall. The calm is so absolute that it often traps unwitting travelers. Migratory birds caught in the outer bands often fight their way inward until they break through to the tranquility of the eye. Once inside, they find themselves unable to penetrate the high-velocity winds of the eye wall to escape back out. They are effectively captured, forced to travel with the storm for hundreds of miles, circling inside a cage made of wind until the storm eventually dissipates over land. It is a reminder that the eye is not merely empty space. It is the axis upon which the entire chaotic system turns, a geometric necessity, proving that for the rim of the wheel to spin, the hub must remain still. Yet, for all their mathematical precision, we humans have always struggled to relate to these systems through numbers alone. We possess a deep psychological need to personify the forces of nature, to give a handle to the chaos so that we might better understand it. Before satellite imagery could track a hurricane from its birth off the coast of Africa, communities relied on oral history and religious calendars to identify these visitors. In the Caribbean, for hundreds of years, a hurricane was traditionally named after the Roman Catholic saint whose feast day coincided with the storm's arrival upon the islands. There were multiple storms named San Felipe, for instance, distinguished only by the year of their landfall, marking history not by dates, but by the saints who watched over the destruction. This practice of naming eventually evolved from religious reverence to something more practical and occasionally more whimsical. In the late 19th century, a meteorologist named Clement Wragge began naming storms in the southern hemisphere using the Greek alphabet, followed by names from Polynesian mythology. But Wragge is perhaps best remembered for a more mischievous method. He eventually began naming storms after politicians who had cut his funding. This allowed him to publicly describe a storm as erratic, wandering aimlessly, or causing great distress, while technically speaking about a weather system bearing the name of a government official he disliked. While Wragge's humor was unique, the necessity of clear communication during the Second World War brought about a more standardized approach. Air Force and Navy meteorologists, needing to clarify maps across vast oceans, began informally naming storms after their wives and girlfriends. It was a way to bring a touch of home into the sterile, dangerous theater of war. This informal habit proved far more effective than the clumsy use of latitude and longitude coordinates, which were prone to errors in transmission.
It is, after all, much easier to warn a population about a storm named Alice than it is to convey the urgency of a system located at 25 degrees north and 80 degrees west. This led to the formal adoption of female names for Atlantic storms in the early 1950s, a convention that held for decades until the practice was modernized to include male names in 1979. Today, the World Meteorological Organization maintains strict lists of names that rotate every 6 years. The list used in 2024, for example, is the same list that was used in 2018. However, the continuity of this cycle is occasionally broken by the weight of history. When a storm is particularly deadly or causes catastrophic damage, its name is retired from the list forever. It is a somber ritual, similar to retiring a jersey number in sports, but done out of respect for the victims and to avoid future confusion. Names like Katrina, Andrew, and Sandy have been permanently stricken from the rotation, replaced by new names, ensuring that the specific identity of those disasters remains unique in the historical record. Even the use of the Greek alphabet, once the backup plan for busy seasons, has been abandoned in favor of a supplementary list of names, ensuring that every storm, no matter how late in the season, possesses a human identity. While we bestow these systems with names to track them, the ocean feels them simply as a massive transfer of kinetic energy. When a major storm churns across the deep sea, a fascinating interaction occurs between the atmosphere and the water's surface, beginning with the sheer weight of the air itself. Inside the eye of a hurricane, the atmospheric pressure drops significantly, creating a partial vacuum. Because the air pressing down on the ocean is lighter than usual, the water is able to rise, bulging upward in a gentle dome purely because there is less weight holding it back. This phenomenon, known as the inverse barometer effect, acts almost like a straw gently sucking the ocean surface upward, causing the sea level near the eye to rise by several feet. However, the true muscle of a storm does not come from this suction, but from the friction of wind against water. As hurricane-force winds scour the surface, they do not merely slide across it, they grip the water, creating drag. This friction piles the water up in front of the storm's path, acting like a massive, invisible plow pushing a mound of liquid ahead of it. This wind-driven accumulation is what meteorologists call a storm surge. Unlike a standard wave that breaks and retreats, a surge behaves more like a rapid, unnaturally high tide that continues to rise relentlessly. When this moving dome of water encounters the shallow floor of a continental shelf, the water has nowhere to go but up, amplifying the height of the sea until it swallows the coastline. Thinking about the immense power of the atmosphere might make you consider the environment outside your own window right now. I'm curious to know which type of weather you find most conducive to deep sleep. Do you prefer the heavy, rhythmic drumming of rain against the glass, or do you rest better listening to the soft, dry whistling of wind through the trees? Feel free to share your preference in the comments. Regardless of the weather conducive to your rest, out on the open ocean, the wind requires distance to build its true masterpieces. This distance is known as the fetch. The longer the wind blows over an uninterrupted stretch of sea, the more energy creates friction, and the larger the waves become. In the chaotic heart of a storm, these waves do not always behave in a predictable, rhythmic fashion. Occasionally, different wave trains traveling at different speeds and angles will converge. When the crest of one large wave aligns perfectly with the crest of another large wave, they do not cancel each other out. Instead, they combine their heights through a process called constructive interference. This brief mathematical synchronicity births what is known as a rogue wave. For centuries, sailors shared terrified whispers of these sudden walls of water, and for just as long, scientists dismissed them as tall tales born of sea madness. It was only when modern satellite measurements confirmed their existence that we realized the ocean is capable of spontaneously stacking energy, creating transient mountains of water that can reach heights of 100 feet before collapsing back into the dark, churning rhythm of the deep. To understand this churning rhythm, we must look to the invisible architect that sculpts the waves, the force that we cannot see but can only measure by the chaotic fingerprints it leaves upon the world.
For centuries, sailors struggled to agree on how to describe the wind, as one captain's gentle breeze might be another's stiff gale, leading to confusion in logbooks and danger on the high seas. It was only in 1805 that an Irish hydrographer and officer in the British Royal Navy, Sir Francis Beaufort, brought order to the air by creating a standardized scale that married the poetic language of the sea with scientific observation.
The Beaufort scale, as it came to be known, was originally designed not around anemometers or wind speed gauges, but around the behavior of a standard British man-of-war ship and its massive canvas sails. The scale is a ladder of 13 rungs, ranging from 0 to 12, each step describing exactly how the ship and the sea react to the mounting energy of the storm. It begins at force 0, a designation of total peace known simply as calm, defined by the observation that smoke rises vertically from a pipe or chimney, and the sea surface is smooth and reflective, like a polished mirror. As the wind begins to wake, we climb to force 1, or light air, where the smoke drifts but weather vanes remain motionless, and the water shows only the shyest ripples with the appearance of fish scales. By the time we reach force 4, the moderate breeze, the ocean begins to show its teeth. Small waves become longer, and we see the first fairly frequent appearance of white horses, the scattering of foam that breaks the blue. This scale is remarkable because it relies entirely on sensory details, asking the observer to watch the world rather than a dial. When the wind strengthens to force 8, we officially enter the territory of the gale, a word that carries a specific weight in nautical history. In a gale, the wind tears the crests off the waves, sending spindrift, a fine white spray, streaking across the water in long parallel lines. The behavior of the ship changes here as well. In Beaufort's original terms, a gale required the ship to shorten its sails significantly to survive the pressure. The sound of the wind in the rigging shifts from a whistle to a scream, and the sea begins to pile up into moderately high waves of considerable length. At the very top of the scale, at force 12, lies the hurricane, a condition where the air is filled with foam and spray, reducing visibility to almost nothing, and the sea is completely white with driving spray. Even today, despite our satellites and Doppler radar, marine forecasts still rely on this 19th century system of observation, preserving the human connection to the elements, where a storm is defined not just by a number, but by the way it turns the surface of the ocean into a landscape of rising white foam. As we drift away from the tropical nurseries of cyclones and move toward the gray, churning waters of the mid-latitudes, the character of the storm shifts entirely, becoming something sharper and colder. In the winter months, particularly along the eastern seaboard of North America, the atmosphere concocts a different kind of giant, known as the nor'easter, a storm born not of uniform heat, but of distinct and volatile contrast. While tropical storms rely on the warmth of the water itself, these winter Goliaths are fueled by a clash of titans, specifically the collision between the freezing, dry air plunging down from the Canadian Arctic and the warm, steam-like breath of the Gulf Stream flowing up from the south. The name itself is a matter of perspective, derived not from where the storm is going, but from the direction of the punishing winds that slam onto land from the northeast, spiraling inward toward the low-pressure center just offshore. When these opposing air masses meet, usually off the coasts of the Carolinas or New Jersey, the physics of the atmosphere can become unstable very quickly. This phenomenon is mathematically defined by a very precise measurement. The storm's central pressure must plummet by at least 24 millibars in 24 hours. To understand the scale of this, imagine atmospheric pressure as the weight of the air pressing down on the ocean. When that weight vanishes so suddenly, it creates a massive vacuum that causes the surrounding air to rush inward with tremendous velocity, spinning the system into a frenzy.
Unlike the tight, symmetrical spiral of a hurricane with a clear eye, a bomb cyclone often sprawls out in a massive, ragged comma shape, stretching its tail of snow across thousands of miles of ocean and land. These systems are technically called cold core lows, meaning the coldest air resides high above the storm's center, a stark mechanical difference from the warm towers of a tropical cyclone. Because they thrive on the temperature difference between the ocean and the land, these storms are frequent between September and April, turning the ocean's surface into a chaotic mix of freezing spray and gray swells. They are notorious for their persistence. While other storms might race across the map, nor'easters often stall or even move backward in a process called retrogression, pinned against the coast by high pressure blocks in the Atlantic. This slow grind allows them to sit over the ocean through multiple high tides, piling water against the shore and reshaping beaches with heavy erosion, creating a rhythmic pounding that can be felt through the ground miles inland. There is a specific kind of silence that comes after such a storm covers a landscape in heavy, wet snow, a muffled quiet that feels almost ancient. Have you ever experienced the unique, heavy silence of a massive snowstorm where you live? Or do you prefer the rhythmic sound of rain on the roof to help you sleep?
Inside the heart of these winter storms, there is sometimes a phenomenon known as a sting jet, a narrow core of intense winds that descends from miles above the surface, stinging the ocean with hurricane-force gusts before dissipating, proving that even in the coldest waters, the atmosphere retains a focused and formidable power. Yet, as we move from the violent seas where sting jets roam to the frozen interior of the land, the storm changes its character entirely, often trading the roar of the waves for a profound and heavy silence. There is a specific acoustic quality to a landscape blanketed in fresh snow, a hushing of the world that feels almost magical, though the reason is purely physical and deeply comforting. Freshly fallen snow is composed of ice crystals, but structurally it is mostly air. In fact, a layer of fresh, uncompacted powder can be up to 90% trapped air, held within a delicate lattice of ice. This porous structure makes snow an incredibly efficient acoustic absorber, functioning much like the foam padding used in recording studios. When sound waves travel over a snowy field, they dive into the microscopic gaps between the crystals and are trapped there, their energy dissipating into the ice rather than bouncing back to your ears. High-frequency sounds, which usually carry the sharpest noises of a city or a forest, are absorbed most easily, leaving behind only the lower, duller tones. This is why a walk during a snowfall feels so private and enclosed. The storm is literally dampening the vibrations of the world, turning the ground into a massive mute button that insulates you from the chaos of everyday life. However, this tranquility can be deceptive, for the silence of snow often accompanies the blinding chaos of a blizzard. It is a common misconception that a blizzard is defined by the amount of snow that falls from the sky. You might be surprised to learn that in the strict meteorological definition, the volume of falling snow is actually irrelevant. To officially classify a winter storm as a blizzard, the criteria are entirely about wind and visibility. The wind must exceed 35 miles per hour, and the visibility must drop to less than a quarter of a mile for at least 3 consecutive hours. This means that a blizzard can occur even when the sky is perfectly clear of clouds, simply by the wind picking up loose, powdery snow that fell days ago and whipping it across the plains, a disorientation known as a ground blizzard. The intensity of this whiteout and the subsequent silence that follows when the wind dies down often depends on the specific shape of the snowflakes themselves. When the humidity is high and the temperature hovers just a few degrees below freezing,
water vapor crystallizes into the most iconic and complex shape of all, the dendrite. Dendrites are the classic star-shaped snowflakes with 6 branching fern-like arms that spread out symmetrically from a center point. These intricate arms are essential for that deep, quiet accumulation we associate with heavy storms. Because the branches of a dendrite are wide and flat, they act like tiny parachutes, falling slowly and swaying through the air. When they land, their arms interlock with one another, much like the hooks and loops of Velcro, creating a structure that takes up a vast amount of space with very little actual ice mass. This chaotic stacking of star-shaped crystals creates the fluffiest, deepest piles of snow, maximizing the air pockets that silence the world and creating that soft, muffled atmosphere where the only sound you might hear is the rhythm of your own breathing. Yet, distinct from that profound hush, there exists a rare atmospheric event that seems to contradict the very nature of winter. A paradox where the tranquility of falling snow is interrupted by the rumble of the atmosphere. This phenomenon is known as thundersnow, and while it shares the convective energy of a summer thunderstorm, the acoustics of the experience are entirely unique to the frozen season. When thunder rolls during a typical rainstorm, the sound waves travel unimpeded, bouncing off hard surfaces and echoing for miles. But in a heavy snowstorm, the physics of sound are altered. Those millions of descending snowflakes act as acoustic baffles, dampening the sound waves and absorbing the higher frequencies. Consequently, the thunder produced during a snowstorm doesn't crack or rumble across the horizon. Instead, it is often heard as a muted, low-frequency thud, a sound that feels surprisingly intimate and contained. Because the snow insulates the sound so effectively, you generally must be within 2 miles of the lightning strike to hear the thunder at all, making the experience exceptionally rare and localized. While snow muffles the world, another form of winter storm transforms the landscape into something brittle and resonant. The formation of freezing rain creates one of the most visually complex environments in meteorology. Resulting from a specific atmospheric sandwich where falling snow passes through a warm layer of air, melts into rain, and then continues downward into a shallow layer of sub-freezing air just above the surface. In this final stage, the water droplets become supercooled, meaning they remain in a liquid state despite their temperature dropping below the freezing point of 32 degrees Fahrenheit.
These drops are in a state of suspended animation, waiting only for contact with a solid surface to complete their phase change. The moment a supercooled drop strikes a tree branch, a utility wire, or a blade of grass, it instantly crystallizes, releasing a tiny amount of latent heat and turning into a clear coating of ice. Unlike sleet, which freezes into pellets before hitting the ground and bounces with a dry hiss, freezing rain accretes, meaning it builds up in layers of smooth, transparent glaze. This accretion process can coat every distinct needle on a pine tree in a perfect individual casing of ice, preserving the geometry of the forest inside a heavy, transparent shell. When the storm clears and the sun returns, the optical effect is blindingly brilliant, as the landscape acts as a massive prism, refracting light in every direction. The silence of the snow is replaced with a new soundscape in these conditions, characterized by the gentle, glass-like chiming of ice-coated branches swaying in the breeze. It creates a frozen forest that looks imperishable and still, yet is constantly shifting under the immense weight of the water that has been locked into solid form, turning the organic world into a temporary sculpture garden of crystal and light.
From that frozen silence, the mood of the atmosphere can shift entirely, trading moisture for grit and turning the air itself into a solid, opaque force. In the arid regions of the world, water is not the primary architect of the storm. Instead, it is the earth itself that rises up. These are the dust storms, events that feel almost biblical in their magnitude, known in their most intense iterations as haboobs. A haboob is not merely a windy day in the desert, it is a gravity current, a coherent wall of sand and dust that can tower thousands of feet into the air, traveling across the landscape like a moving mountain range. Unlike a typical gale that might simply kick up loose dirt, a haboob is often born from the death of a thunderstorm, where a column of cold, dense air rushes downward, hits the hot ground, and explodes outward, scooping the desert floor up with it. It creates a rolling front that swallows everything in its path, turning bright midday sunlight into a deep, rust-colored twilight. If you have ever watched a storm roll in from the safety of a porch or a window, you know the specific anticipation of seeing the horizon change color. But a dust storm changes the very texture of the air you breathe. Have you ever experienced a weather event that completely changed the color of the sky, perhaps making you feel as though you were walking on the surface of another planet? While the wind provides the forward momentum for these storms, there is a quieter, invisible force that helps these particles defy gravity. Science tells us that electrostatic forces play a crucial, hidden role in the life of a dust storm. As grains of sand bounce and collide across the surface, a process geologists call saltation, they generate friction. This constant rubbing creates a static charge, similar to a balloon rubbing against wool. The smaller dust particles often become negatively charged, while the ground remains positive, creating a strong vertical electric field that can actually lift dust particles into the air, suspending them in a haze of charged earth, even when the wind momentarily lulls. These storms are not just local spectacles, they are planetary couriers operating on a massive scale. One of the most poetic realities of our climate system involves the transoceanic journey of dust from the Sahara Desert, specifically from a dried-up ancient lakebed in Chad known as the Bodele Depression. This single location is often cited as the dustiest place on Earth. The storms here lift mineral-rich dust high into the upper atmosphere, where it catches the trade winds and begins a journey of several thousand miles across the vast blue expanse of the Atlantic Ocean. It is a river of earth flowing through the sky, and its destination is the Amazon rainforest. This dust is laden with phosphorus, a nutrient that is crucial for plant growth, but is constantly washed away by the heavy rains in South America. In a remarkable twist of geological fate, the amount of phosphorus lost by the Amazon soil each year is almost exactly replaced by the phosphorus dropping from the sky, carried there by African dust storms. The lungs of our planet are effectively fertilized by the ancient, dusty skeleton of a desert lake. It is a profound reminder that the Earth is a single, breathing organism, where a blinding storm on one continent is the breath of life for a forest on another. Yet, if we cast our imagination beyond the thin blue line of our own atmosphere, leaving the familiar biological rhythms of Earth behind, we find that the solar system holds tempests that defy our terrestrial understanding of scale and time. Out in the cold, silent vacuum, past the rocky belt of asteroids, spins the king of planets, Jupiter.
This is a world composed almost entirely of weather, a gas giant where there is no solid ground to stand upon, only bands of clouds stretching thousands of miles deep, whipped into distinct stripes of cream, ochre, and rust by jet streams that never cease.
Dominating this swirling, marbleized sphere is the solar system's most famous atmospheric phenomenon, the Great Red Spot. It is difficult to truly comprehend the sheer magnitude of this ancient storm. When viewed through a backyard telescope, it appears as a mere blemish, a crimson eye staring back at us from the gas giant's southern hemisphere. But up close, it is a monster of incomprehensible proportions. At its widest point, this single storm is large enough to swallow the entire planet Earth whole. Historically, it was even larger, once wide enough to contain 2 or 3 Earths side by side. Imagine for a moment a hurricane so vast that our entire civilization, every ocean, every continent, every forest, and every cloud we have ever known could be dropped inside its boundaries with room to spare, lost within the churning crimson winds. Unlike the storms on Earth, which are typically fueled by warm ocean water and inevitably die out when they drift over land or cooler seas, the Great Red Spot has no land to crash into. It is a storm that effectively feeds itself. Astronomers have been tracking this angry red oval for at least 300 years and perhaps even longer. When the first rudimentary telescopes were pointed at the night sky in the 17th century, observers noted a permanent spot on Jupiter's face. It was raging while empires rose and fell on Earth, spinning while the steam engine was invented, and continuing its violent rotation as humanity learned to fly and eventually reach the moon. It creates a strange sense of awe to consider that something so turbulent can also be so permanent, a chaotic landmark that has outlived generations of stargazers. The physics of this celestial giant are equally mesmerizing. On Earth, our hurricanes and cyclones are low-pressure systems, usually spinning inward. The Great Red Spot is the opposite. It is an anticyclone, a massive system of high pressure. Because it sits in Jupiter's southern hemisphere, it rotates counterclockwise, completing a full rotation roughly 6 Earth days. The winds at its outer edge scream at speeds exceeding 400 miles per hour, significantly faster than the most devastating Category 5 hurricanes on our planet. Yet the center remains somewhat calmer, a high-pressure plateau that rises 8 kilometers higher than the surrounding cloud decks. It is a storm of chemical mystery as well, as scientists still debate exactly what gives the spot its ruddy hue, suspecting that ultraviolet light from the distant sun cooks simple chemicals like ammonia and acetylene in Jupiter's upper atmosphere, turning them into a dark, brick-red smog. While the storms of Jupiter are contained within its gravity, there is a different kind of tempest that rages across the vast vacuum of the solar system, originating from the heart of our own star. The sun is not merely a static ball of light, but a churning ocean of plasma that experiences weather on a scale that defies human comprehension. We call these events solar storms, and they begin with the twisting and snapping of magnetic field lines on the sun's surface. When these magnetic bands break, they can release a coronal mass ejection, or CME, launching billions of tons of solar material into the void. Imagine a cloud of superheated gas, significantly larger than the Earth itself, hurled through the dark silence of space. Unlike the light from the sun, which reaches us in just over 8 minutes, these storms are travelers of substance and weight, taking anywhere from 15 hours to several days to cross the 93 million mile divide between the sun and our planet. Even when the sun is relatively quiet, it is never truly still. It constantly exhales a stream of charged particles known as the solar wind. This wind blows outwards in every direction, moving at speeds that can exceed 1 million miles per hour, filling the space between the planets with a thin, invisible mist of electricity. When this solar gale reaches Earth, it does not strike the surface directly. Instead, it encounters our magnetosphere, a magnetic bubble that acts as a shield against the cosmic barrage. Most of the solar particles are deflected harmlessly, flowing past Earth like water moving around a stone in a stream. However, during a powerful magnetic storm, the solar wind presses hard against this shield, and some of the energetic particles find a way in. They spiral down the magnetic field lines, funneling toward the north and south poles, accelerating until they slam into the atoms of our upper atmosphere. This collision is where the violence of a solar storm transforms into the breathless, ethereal beauty of the aurora borealis. The sky begins to glow not from sunlight, but from the energy released as atmospheric atoms get excited by the collision and then calm back down, emitting photons of light in the process. The colors you see are actually the chemical fingerprints of the air itself, revealing which elements are dancing with the solar wind.
The most common color, a ghostly, vibrant green, is produced by oxygen atoms located about 60 to 180 miles above the ground. It creates those familiar, shifting curtains that seem to fold over one another in the high latitudes. If the solar storm is particularly intense, reaching even higher altitudes beyond 180 miles, that same oxygen emits a rare, deep red glow, creating a crimson wash that hangs at the very edge of space. Below the oxygen, deeper in the atmosphere, nitrogen atoms await their turn. When solar particles strike nitrogen, the sky blooms with shades of blue and purple, sometimes mixing with the green to create a pinkish fringe at the bottom of the dancing lights. These luminous ribbons are the visible echo of a magnetic storm, a silent reminder that our planet is constantly interacting with the breathing star that sustains us. This solar influence stretches far beyond our own atmosphere, touching every world in our celestial neighborhood. Yet the weather it creates elsewhere is often stranger than fiction. If you travel outward to the gas giants, the familiar spirals of Earth's hurricanes are replaced by geometry that defies simple explanation. At the North Pole of Saturn, there exists a storm that has been spinning for decades, perhaps even centuries, not in a circle, but in the shape of a perfect hexagon. This six-sided jet stream is a colossus of the outer solar system, a geometric crown spanning 20,000 miles across, wide enough to cradle 4 Earths side by side within its cloudy walls. While our storms are chaotic and wandering, Saturn's hexagon is eerily stable, rotating in sync with the planet's interior, a persistent reminder that the laws of fluid dynamics can produce startling order out of chaos. Inside this hexagonal boundary, the winds are turbulent, yet the shape itself holds firm, changing color from a bluish haze to a golden hue as the long Saturnian seasons slowly shift from winter to summer. It is a storm that looks as though it were drawn by a draughtsman's ruler rather than the wild forces of nature. Drifting even further into the dark, cold reaches of the system, we find Neptune, an ice giant that appears serene from a distance but hides a turbulent secret. Despite being so far from the sun's heat, Neptune hosts the fastest winds in the solar system, whipping through the upper atmosphere at supersonic speeds, reaching 1,200 miles per hour. In this frozen twilight, the pressure becomes so immense deep within the slushy mantle that scientists believe it literally rains diamonds. The carbon in the atmosphere is crushed until it crystallizes, creating a glittering, precious precipitation that sinks slowly towards the planet's core in a silent, unseen shower of riches. When you look up at the night sky, do you ever find yourself wondering what the weather is like on those distant points of light? Or do you simply enjoy the beauty of the stars themselves? I would love to hear what goes through your mind when you gaze upward into the vastness. Closer to home, the weather presents a different kind of grandeur on the red planet. Mars is famous for its dust storms, but unlike the localized hababoobs of Earth's deserts, Martian storms can grow to encompass the entire planet. Because the atmosphere is so thin, the dust is as fine as cigarette smoke, easily lifted and suspended for weeks at a time.
Every few years, these storms merge until a singular global veil of red dust obscures the surface completely, turning the planet into a featureless sphere. When the Mariner 9 spacecraft arrived in 1971, it was greeted by one of these planet-wide events, with only the peak of Olympus Mons, the tallest volcano in the solar system, piercing through the dusty haze like an island in a rusty sea. These storms generate so much static electricity that they likely crackle with invisible lightning, a dry electric fury that scours the rocky surface before eventually settling into a fine, powdery stillness. While the storms of Mars rage in a lifeless void, here on Earth the atmosphere is alive, and the creatures that dwell within it are attuned to every whisper. Before the first dark clouds gather on the horizon, the animal kingdom often knows that the sky is changing. We humans rely on radar, satellites, and barometers to tell us when to carry an umbrella, but the biological sensors of the natural world have been refining their accuracy for millions of years. Consider the birds, particularly the golden-winged warbler. In a remarkable event that stunned ornithologists, a population of these tiny birds in Tennessee completely evacuated their breeding grounds days before a massive tornado outbreak occurred. The storm was hundreds of miles away, completely invisible to the naked eye, yet the birds fled. The secret lies in infrasound. Severe storms generate low-frequency sound waves that travel immense distances, rippling through the atmosphere like unseen waves in a pond. These sound waves are far too low for human ears to detect, falling below 20 hertz. But for birds, this infrasound is a siren. They can hear the deep, rhythmic rumble of a tempest from across state lines.
It is a sensory connection to the sky that we can scarcely imagine. A physical feeling of the air vibrating with a warning long before the wind begins to howl. As we lower our gaze from the sky to the rolling pastures, we encounter one of the most persistent pieces of weather folklore, the belief that cows lie down before it rains. It is a gentle, pastoral image, suggesting that the herd is settling in to keep a patch of dry grass for themselves. While there is a grain of truth here, the reality is more biological than meteorological. Cows primarily lie down to chew their cud or to regulate their body temperature. Standing up exposes more surface area to the air, which helps them cool down. However, as a storm approaches, the air pressure drops and the heat often rises before the break, making the ground cooler than the air. So a herd lying down might be reacting to the humidity or the heat index rather than predicting the rain itself. Still, there is a quiet wisdom in observing a field of cattle at rest, their heavy breathing syncing with the heavy, humid air of an approaching front. But perhaps the most profound reactions occur where we cannot see them at all, beneath the surface of the waves. Water is much denser than air, and the pressure changes associated with hurricanes can be felt deep in the ocean. Sharks, specifically black-tipped sharks, act as living barometers. They possess a sensitive lateral line system and an inner ear capable of detecting minute changes in hydrostatic pressure. When a hurricane is still far out to sea, the drop in atmospheric pressure reduces the weight pressing down on the ocean's surface. Sharks sense this shift and instinctively head for deeper water, fleeing the turbulent shallows where they might be battered by the coming surge. It is a migration driven by the physics of the storm, a silent retreat into the dark, calm depths while the surface world prepares for the wind. While the shark retreats into the hydrostatic safety of the deep, the trees upon the shore have no choice but to stand their ground and face the atmosphere's fury head-on. The adaptation of flora to high winds is one of nature's most sophisticated feats of engineering, a silent battle of physics that takes place in every forest during a gale.
trees are not merely static statues made of wood. They are dynamic, responsive structures that have evolved to treat the wind not just as an adversary, but as a shaping force. When the first heavy gusts slam into a deciduous forest, the broadleaf trees engage in a defensive maneuver known as reconfiguration. This is a form of aerodynamic streamlining. Leaves, like those of the oak or maple, do not simply flap chaotically. They are designed to curl into tight, cone-like shapes, folding in on themselves to reduce their surface area by nearly half. This effectively lowers the drag coefficient of the entire canopy, allowing the violent air to slip past the branches rather than pushing against them with full force. However, the true master of storm survival is the palm tree. Its resilience is legendary, but the science behind it is purely mechanical. Unlike an oak or a pine, a palm tree is not technically wood in the traditional sense. It's a monocot, more closely related to grass than to timber. It lacks the rigid, concentric growth rings that make other trees stiff. Instead, its trunk is composed of fibrous, spongy bundles that allow for extraordinary flexibility. A palm can bend almost 50 degrees without snapping, swaying in a rhythmic dance that would shatter rigid hardwood. The large fan-like leaves are heavy and catch the wind like sails, which puts immense torque on the trunk. In the midst of a hurricane, the palm is biologically programmed to let these fronds snap off. By shedding its leaves, it instantly dumps the wind load, sacrificing its solar panels to save the central column of life. It is a calculation of loss for the sake of survival. This resilience is not accidental, it is learned. The constant mechanical stress of the breeze signals the tree to produce reaction wood, a specialized, denser type of cellulose that reinforces the trunk on the side taking the strain. A tree grown in a greenhouse, protected from every breeze, will often collapse under its own weight if moved outside, because it never faced the minor struggles that build the strength required for the major storms. Yet even the strongest trees sometimes fall, and here the storm plays its final ecological role through lightning. When a massive canopy tree is struck and shattered, it brings destruction, but it also brings life. In dense forests, the canopy is so thick that sunlight rarely touches the ground. The storm tears a hole in this dark roof, a process called gap dynamics. Suddenly, a column of light floods the forest floor, waking up seeds that have lain dormant in the soil for decades, waiting for the giant to fall. The storm does not just remove the old, it clears the stage for the new.
It is no wonder that before we understood low-pressure systems and convection currents, we looked up at this violent renewal and saw the hands of the divine at work. When the sky turned black and the air grew heavy, early humans did not see a drop in barometric pressure, they felt the presence of a conscious being. For thousands of years, the storm was not a meteorological event, but a conversation between the heavens and the earth, often spoken in a language of anger or protection. In the ancient Greek imagination, the sky itself was ruled by Zeus, the cloud gatherer, whose mood dictated the weather. When the dark clouds rolled over Mount Olympus, it was believed he was shaking his aegis, a shield that produced the roar of thunder to terrify his enemies, while the lightning bolt was his personal weapon, forged by the Cyclopes to maintain order in the cosmos. To the north, the Vikings heard a different story in the crashing skies. For them, the deep rumble of thunder was the sound of heavy iron chariot wheels rolling across the clouds, pulled by two massive goats. The driver was Thor, the red-bearded protector of humanity, who wielded Mjolnir, the short-handled hammer that always returned to his hand after being thrown.
It was said that lightning was the spark flying from his hammer as it struck the skulls of frost giants, protecting the realm of Midgard from the chaotic forces of ice and winter. This idea of the storm as a cosmic battle is a thread that weaves through almost every culture. In Vedic mythology, the god Indra, often associated with storms and rain, fought a great dragon named Vitra who had stolen all the world's water and trapped it inside a mountain. By defeating the serpent with his thunderbolt, Indra cracked the mountain open, releasing the captive rains to nourish the parched earth below. Across the Pacific, Japanese folklore tells of Raijin, a terrifying yet respected spirit who beats upon drums to create thunder, often paired with Fujin, the god of wind who carries a large bag of air on his shoulders. Legend says that during the Mongol invasions of Japan in the 13th century, these gods summoned a massive typhoon known as the kamikaze, or divine wind, which destroyed the invading fleet and saved the islands, cementing the storm's reputation as a guardian of the nation. In the beliefs of many indigenous peoples of North America, the storm is embodied by the thunderbird, a supernatural creature of enormous power and strength. It is said that the flapping of its wings causes the thunder, and the flashing of its eyes creates lightning, hunting the great horned serpents of the underworld to keep the balance of nature in check. Perhaps most fascinating is the linguistic legacy left by the Mayan god of the storm, Huracan. He was one of the creator deities who participated in building the universe, existing in the mist and the primordial waters. It was believed he possessed the power to summon the great flood and control the winds. When Spanish explorers encountered the terrifying tropical cyclones of the Caribbean, they adopted the indigenous word for these evil winds, giving us the modern term hurricane, a lasting reminder that our language for storms is deeply rooted in the sacred fears of the past. This reverence was well-founded, for history is littered with moments where the sky itself seemed to intervene in human affairs, altering the destiny of nations with a single gust. One of the most famous examples of this atmospheric intervention occurred in the late 13th century, involving the Mongol Empire, which was then the largest contiguous land empire in history. Kublai Khan, the grandson of Genghis Khan, had set his sights on conquering Japan, assembling a massive fleet that was poised to overwhelm the samurai defenses. In 1274, the Mongols landed, but just as the battle turned against the Japanese defenders, a severe typhoon rose from the sea, wrecking the Mongol fleet and forcing a retreat. Remarkably, history repeated itself 7 years later in 1281, when the Khan returned with an even larger force. Some accounts suggest over 4,000 ships and 140,000 men. Another massive typhoon struck at the exact moment the fleet was most vulnerable. The storm decimated the armada, saving Japan from occupation. The Japanese people believed the gods had sent the storm to protect them, coining the term kamikaze, or divine wind, a phrase that has echoed through the centuries as a testament to the storm's power to dismantle the plans of emperors. Have you ever felt a sudden change in the weather that seemed to perfectly match the mood of a moment in your own life? Centuries later, on the other side of the globe, the wind would once again decide the fate of an empire. In 1588, King Philip II of Spain launched the Spanish Armada, a fleet so grand it was termed invincible, intended to conquer England and overthrow Queen Elizabeth I. While English naval tactics played a role in the initial skirmishes, it was the weather that delivered the final blow.
As the Spanish fleet attempted to flee by sailing north around Scotland and Ireland, they were met by unseasonably fierce gales in the North Atlantic. The sophisticated Spanish galleons, designed for the calmer waters of the Mediterranean, were battered by the relentless waves of the Irish coast. Dozens of ships were wrecked, and thousands of sailors were lost not to enemy fire, but to the raw fury of the sea. These newly formed nitrates dissolve into the falling rain,
descending to the soil as a nutrient-rich natural fertilizer. This is why, after a violent summer storm, the grass and forests often appear a deeper, more vibrant shade of green than they do after a simple watering from a garden hose. The storm has quite literally fed the earth from the sky. This process of renewal extends to the air itself, which often feels heavy and stagnant before the clouds break. The descending rain acts as a massive atmospheric scrubber, capturing dust, pollen, and suspended pollutants, dragging them down to the ground and leaving the atmosphere scrubbed clean. There is a distinct sensory shift that occurs once the thunder fades and the final drops fall, a change in the very texture of the air that many find deeply comforting. It begs the question, do you find that the world feels lighter to you after a storm passes, giving you a sense of clarity and freshness that makes it easier to rest? While we often perceive these events as chaotic interruptions to our lives, on a planetary scale, a storm is actually a mechanism of balance and order. The Earth is heated unevenly by the sun, with the equators soaking up the vast majority of the solar energy, while the poles remain cool. Without a way to redistribute this massive accumulation of heat, the tropical regions would become unbearably hot, and the poles would freeze into solid, lifeless blocks of ice. Storms, particularly large cyclones and hurricanes, function as the planet's global thermostat. They act as giant heat engines, absorbing the warm, moist energy from the tropical oceans and transporting it toward the poles, dissipating the excess heat into the upper atmosphere and cooler latitudes. This redistribution is essential for maintaining the moderate climate zones where most life thrives. Furthermore, the violence of the rain is often the only way to replenish the deep water tables that lie far beneath the surface. While a gentle drizzle might only dampen the topsoil, the sustained heavy soak of a major storm system drives water deep into the bedrock, refilling the ancient aquifers that feed our springs and wells, ensuring that even when the skies clear and the sun returns, the life below continues to drink. While the roots of the forest drink from this newfound groundwater, there is a different kind of activity happening on the paved roads nearby, where headlights cut through the gloom. Most living things seek shelter when the pressure drops and the sky turns the color of a bruised plum, but there is a unique subset of humanity that does the exact opposite. Storm chasing is a discipline that exists at the intersection of hard science and profound wonder, driven by a deep instinctual curiosity to understand the behavior of the atmosphere when it is most agitated. To study these tempests effectively, scientists cannot simply observe from the safety of a distant laboratory. They must take their instruments into the field, closing the distance between themselves and the wind. This necessity led to the invention of robust ground-based sensors, some of which are famously known in the meteorological community as turtles. These are small, heavily armored instrument packs designed with a low aerodynamic profile and a heavy lead lining to keep them anchored to the ground. The objective is to place these sensors directly in the path of a tornado or a severe downdraft, allowing the storm to pass right over them. While the scientists retreat to safety, the turtle remains behind, its internal sensors recording barometric pressure, humidity, and wind speed at the very surface of the Earth, gathering data that radar, which scans higher up in the sky, simply cannot see. It is a way of listening to the heartbeat of the storm from the inside, measuring the rapid pressure deficits that tell us how tornadoes breathe and maintain their structure. But for many who travel these long miles across the open plains, the reward is visual as much as it is numerical. The structure of a mature supercell thunderstorm is often compared to a living sculpture. Observers look for the mesocyclone, the rotating updraft that powers the storm, which can often resemble a stacked plate or a massive spinning barber pole stretching thousands of feet into the air. Have you ever found yourself sitting by a window or on a covered porch, mesmerized by the sheer scale of a thunderhead building in the distance, feeling a strange sense of peace amidst the power? That feeling is what drives the appreciation of storm structure.
There is a specific eerie beauty to the colors that manifest during these events. You might witness the sky turning a deep aquatic green, a phenomenon that occurs when the reddish hues of a setting sun are scattered through heavy concentrations of water droplets and hail suspended high within the cloud tower. It's a vivid reminder that the atmosphere is a fluid, behaving much like the ocean, full of currents, eddies, and waves that just happen to be made of air rather than water. Capturing these moments requires patience and a respect for the forces at play.
The photographers and researchers who document these events are cataloging the mood swings of our planet, freezing the chaotic motion of the wind into a single, breathtaking frame that reveals the intricate, almost architectural organization of the clouds. Through their lenses and their sensors, we learn that the storm is not just a disordered mess of wind and rain, but a highly organized heat engine trying to balance the energy between the warm Earth and the cold upper atmosphere, performing a necessary function for the planet's climate with sublime elegance. And when that elegant engine finally winds down, it leaves behind a world that feels fundamentally changed, scrubbed clean by the turbulence, and restored to a state of pristine clarity. This sensation of freshness is not merely poetic imagination, but a chemical reality, as storms generate massive amounts of negative ions, which act to clear the air of dust, mold spores, and pollen, contributing to that crisp, invigorating feeling we experience when we open the window after the rain. Accompanying this atmospheric freshness is the distinctive, earthy scent that rises from the pavement and the soil, a phenomenon known as petrichor, a term constructed from the Greek words for stone and the ethereal fluid that flows in the veins of the gods. This beloved scent arises chiefly from a compound called geosmin, released by soil-dwelling bacteria called actinomycetes when the raindrops hit the ground, producing a chemical signal so potent that the human nose is sensitive to it at just 5 parts per trillion, making us far more sensitive to the smell of rain than a shark is to blood in the water. As the heavy gray curtains part and the light returns, the landscape often appears significantly more vibrant and lush, a transformation aided by the lightning itself, which possesses the energy to break apart the strong bonds of nitrogen molecules in the atmosphere. These atoms mix with oxygen and dissolve in the rain, falling to the ground as nitrates, a natural fertilizer that literally greens the earth with every strike, proving that the storm is a giver of life just as much as it is a display of power. Even the soundscape of the world shifts, moving from the roaring cacophony of thunder to a profound, heavy stillness, where the only noise is the rhythmic dripping from leaves and eaves, a natural lullaby that marks the return of peace. We have journeyed far in our exploration of these atmospheric giants, tracing the narrative of the storm from the microscopic coalescence of water vapor on a single speck of dust to the towering anvils that scrape the bottom of the stratosphere. We have followed the path of the hurricane, spiraling across the warm ocean, stood in the shadow of the supercell, and looked upward at the enduring mystery of the great red spot, spinning silently in the vacuum of space. Through it all, we see that whether on Earth or on distant gas giants, storms are the heartbeat of a planet's climate, the great redistributors of heat and energy that strive for equilibrium in a chaotic universe. They are the mechanism by which the atmosphere breathes, inhaling warmth and moisture and exhaling the weather that shapes our lives. And now, as the imaginary thunder rolls away into the distance, fading into a gentle rumble on the horizon, you are left in the most perfect state of all, safely sheltered, warm and dry, while the natural world outside continues its eternal, rhythmic cycle. The drama of the wind has ceased, and the air is absolutely still. This final quietude is the ultimate gift of the weather, a gentle reminder that every disturbance is temporary and that tranquility always returns to those who wait. As you drift deeper into this calm, letting the knowledge of the wind and rain settle into your dreams, remember that the storm has done its work and now it is time for you to rest. There are always more stories to tell and more wonders to explore in the safety of sleep. If you have found comfort in this journey through the clouds and wish to return for more relaxing facts and soothing science, please subscribe to our channel, ensuring that your next rest is just as peaceful and filled with wonder. Good night.